The war in Europe was dying in a blaze of final, desperate resistance and the pervasive smell of burnt cordite. Spring 1945 was not a time of celebration for the Allied forces streaming across the collapsing German landscape. It was a time of cold, focused hunting. The primary mission, now that victory was assured, was to secure the secrets of the Reich, the technological leaps and terrifying new weapons that Adolf Hitler had promised would reverse the tide of history. This mission, codenamed Operation Paperclip by the Americans and similar efforts by the British and Soviets, was a frantic, covert race for intellectual spoils. The targets were not troop formations or fortified cities, but laboratories, factories, and, most critically, the immense paper trail of the Nazi scientific establishment. Teams of specialists, scientists, engineers, and intelligence officers known as T-Force, Target Force, scoured the ruined nation, guided by grainy aerial reconnaissance photos and the last-minute interrogations of captured scientists. They sought jet engines, rocket technology, and, most urgently, any trace of the rumored German atomic program. It was during one such sweep, in the rubble-strewn forests of Thuringia, that a small, highly specialized American intelligence unit made a discovery that would haunt the nightmares of Cold War strategists for decades. The target was a seemingly innocuous, small research facility attached to a complex of chemical plants, an area that had been heavily bombed but hastily abandoned just days before the arrival of the U.S. Third Army. The facility itself was a grim tableau of wartime ruin. It was half-burned, partially flooded, and hastily evacuated. Fire damage scarred the brick exterior, and a ruptured water main had turned the lowest level into a murky, toxic swamp. Desks were overturned, filing cabinets lay open and rifled, and chemical glassware lay shattered on the floor, the scene of a panicked, last-minute destruction effort by the retreating German scientists. The Allied team, led by Major Elliot Stone, an engineering analyst fluent in German, spent 2 days sifting through the wreckage. They recovered routine industrial reports, mundane personnel files, and the usual collection of propaganda leaflets. But Major Stone, guided by a hunch and the smell of industrial sealant, noticed a subtle anomaly in the flooded basement, a section of the concrete floor that appeared unnaturally new and clean compared to the surrounding muck. Using a borrowed German jackhammer, Stone's team breached the slab. Beneath it, encased in a shallow concrete vault, they uncovered a large, sealed metal container. It was not a safe, but a high-specification transport box, designed to protect its contents from humidity, fire, and concussion. The box was stamped with the insignia of the Heereswaffenamt Army Ordnance Office and the highest classification markings of the Reich, top secret, for the Führer's eyes only. The heavy seal was broken with brute force. As the lid creaked open, the air that escaped was dry and sterile, a ghost of the wartime environment that had preserved the contents. Inside lay the intelligence hull of a lifetime, a collection of technical papers, calculations, and, dominating the container, a vast, rolled set of parchment-backed engineering drawings so unusual, so advanced, and so out of alignment with known German wartime capabilities that analysts were shocked. These weren't the V-2 rockets they were familiar with. This was something darker, more ambitious, and, critically, something that confirmed the worst fears the Allied command had secretly harbored about the true extent of the Nazi technological effort. The drawings were meticulously rendered, detailing not a mere weapon, but a complete, complex weapon system, a sprawling, multi-stage project that seemed to defy the very possibility of 1940s technology. The blueprint described a system that, if completed, could have changed the trajectory of the war, and potentially the post-war world. It was a plan that transcended tactical victory. It aimed for a devastating, strategic advantage that would have left Germany unassailable, even in defeat. The analysts, seeing the scale of the power described in the dry, mathematical notations, realized they had not just found a secret weapon, but the core design for an absolute geopolitical game-changer. The blueprints, later catalogued and analyzed under intense secrecy in Washington and London, were given the unofficial designation, the Stone Vault Contents, but the German project name, clearly marked on the title blocks, was chillingly arrogant: Project Weltenhammer, the World Hammer. Weltenhammer was not a single weapon, but a concept, the complete, audacious plan for the Reich's ultimate deterrent, a global reach, multi-stage, intercontinental delivery system. The first stage of analysis focused on the sheer scale of the engineering effort. The schematics detailed a colossal, multi-stage rocket system, far larger than the existing V-2A4. This was designated the A9-A10 system. The A9 was the second-stage winged missile, designed to glide down from the edge of space towards its target. The A10 was the massive booster stage, a clustered engine design, using 7 separate engines to achieve the necessary thrust to break the conventional atmosphere. The fear wasn't the rocket itself. The Allies knew of the V-2 and its successor programs. The terror lay in the calculated range. The specifications indicated a maximum range of approximately 5,000 kilometers, 3,100 miles. This was not aimed at London or Antwerp. This was aimed at the east coast of the United States. The Allied strategists were paralyzed by the realization, had Germany been capable of building this, they could have threatened New York, Washington, and major industrial centers like Detroit. This was the true, terrifying potential of Weltenhammer, to reach across the Atlantic and shatter the American sanctuary, the protected factory of democracy that fueled the Allied war machine. The details of the A9-A10 system were astonishingly modern. The plans included a highly detailed concept for ablative heat shielding, a coating designed to burn away slowly, protecting the main body of the warhead as it re-entered the atmosphere at hypersonic speeds. This was technology decades ahead of its time. A sophisticated liquid oxygen alcohol fuel pump system, designed for maximum efficiency and requiring immense, complex turbopumps. Detailed guidance plans involving star trackers and inertial navigation, primitive precursors to the systems that would eventually guide Cold War ICBMs. The second, even more terrifying revelation involved the payload. The blueprints were vague in the military section, labeled simply, Special Payload Unit, Project Ursa Major. However, accompanying chemical and physics notes, hastily scribbled in the margins, offered the grim context. They detailed the required weight and volume constraints for a fissionable core of a specific density. Major Stone's interpretation, confirmed by the nuclear physicists rushed to the scene, was devastating. The A9-A10 system was designed to be the delivery vehicle for a nuclear weapon. The payload specifications perfectly matched the projected size and weight of a crude, first-generation fission device, the German equivalent of the American Thin Man or Fat Man bomb concepts. The Weltenhammer blueprints, therefore, were not just a missile plan, they were the blueprint for a German nuclear-tipped ICBM. The discovery instantly redefined the final phase of the war. Allied intelligence had long feared a miracle weapon, capable of turning the tide, but they had consistently underestimated the ambition and scale of the German rocketry and nuclear programs. The realization that the Nazis were concurrently pursuing a nuclear weapon and a viable intercontinental delivery system for it was horrifying. The Allied fear, the collapse of sanctuary. For the Allies, particularly the Americans, the blueprint confirmed their darkest anxiety, the collapse of the sanctuary doctrine. The United States had believed itself fundamentally protected by two vast oceans. While Europe suffered V-weapon attacks and constant bombardment, America was safely building the planes, tanks, and ships needed to defeat the Axis. Weltenhammer proved that in another 2 years, perhaps even less, that sanctuary could have vanished. A German nuclear strike on a port like New York or a production hub like Pittsburgh, even with a single, rudimentary device, would have been politically catastrophic, decimating war production and potentially forcing the U.S. government to divert massive resources to continental defense, rather than invasion. The blueprints demanded immediate, absolute secrecy. The decision was made at the highest levels to classify Weltenhammer under a code even higher than that used for the Manhattan Project's intelligence. The public could never know how close the Nazis had come. The narrative of assured Allied victory could not be tainted by the spectral image of a swastika-bearing atomic warhead falling on American soil. The intelligence value of the plans was immense. They immediately became the cornerstone of post-war American and Soviet missile programs. The technical concepts laid out by the captured German engineers became the immediate starting point for the development of the first true ICBMs, the Atlas and Titan missiles for the US, and the R-7 for the Soviets. The V-2 program's ultimate goal was not London, but Washington, and that terrifying vision was now the intellectual property of the victors. The Axis fear, engineering and political madness. While the Allies feared the weapon's potential, the German engineers who designed Weltenhammer lived in their own state of paralyzing fear, the fear of madness and overreach. The engineering drawings contained annotations, hastily scribbled notes, often highly critical, from the project lead, Dr. Hans Muller, a pseudonym used in later classified reports. Muller's notes detailed the crushing technical impossibility of the project given Germany's rapidly deteriorating industrial base. Resource depletion. Muller noted the constant struggle for basic materials, high-grade aluminum, copper for wiring, and, most critically, the massive specialized tools needed to machine the rocket's engines. He wrote, "We design for the sky, but we have no oil for the lathes." Political pressure. The notes vividly described the relentless, irrational pressure from the Nazi high command, particularly from the SS and the Minister of Armaments, Albert Speer, to accelerate the program beyond any rational timeline. The scientists were forced to cut corners, ignore safety protocols, and promise impossible delivery dates. The scale of the lie. The German scientists knew Weltenhammer was a lie, a magnificent piece of theoretical engineering that required a peacetime industrial capacity to build. It was a project designed to serve as a propaganda tool and a psychological deterrent, not a genuine deployable weapon. Yet, they were forced to continue, knowing that failure to deliver on Hitler's final promise would mean execution. The most profound Axis fear was that the Führer would demand the deployment of a partially functional prototype, armed with a chemical or conventional payload, simply to fulfill a promise, sacrificing the entire scientific team and potentially alerting the Allies to the program's true scope. The sealed box containing the blueprints was not just a historical archive, it was a desperate attempt by the chief engineers to preserve the pure technical truth of their design, saving it from the distortion and madness of the collapsing regime. The context for the discovery of the Weltenhammer blueprint was a global, desperate technological free-for-all. By 1944, the war had devolved into a grinding attrition match, but beneath the surface, a hidden race to out-innovate was underway, driven by the knowledge that the next war, the Cold War, would be fought not by infantry but by scientists and engineers. Both Germany and the Allies recognized that conventional superiority was meaningless if the enemy achieved a single, decisive technological leap. In the late war years, both Germany and the Allies were pushing aircraft and weapon designs far beyond established limits. The Reich, facing annihilation, doubled down on its Wunderwaffen wonder weapons program, viewing exotic technology as the only possible salvation. Conversely, the Allies, determined to end the war swiftly and protect their massive bomber fleets, pursued countermeasures and advanced designs with equal zeal. The pace of development was breathtaking. Jet engines, rocket propulsion, swept wings, and guided missiles were developing rapidly. Germany had already deployed the Messerschmitt Me 206, the world's first operational jet fighter, and the V-2 rocket, the first ballistic missile. The Allies, though slower to field jets, had countered with the British Gloster Meteor and were perfecting complex radar and proximity fuses. This was the era where the conventional piston-engine aircraft was taking its final flight, replaced by the roar of the turbine and the silent, terrifying trajectory of the rocket. This period was characterized by a chaotic explosion of conceptual design. Engineers, freed from the constraints of immediate production goals and motivated by sheer desperation, sketched out aircraft that looked utterly futuristic. These ideas were often speculative, constrained by materials shortages and the lack of powerful enough engines. Therefore, intelligence units struggled to determine which designs were viable and which were fantasy. They had to sift through thousands of captured documents, some genuine breakthroughs, some intentional decoys, and some the fever dreams of desperate scientists. The Weltenhammer blueprint, specifically the associated airframe that delivered its specialized payload, appeared to sit somewhere in the middle, too advanced to dismiss outright, yet too ambitious to easily believe. The engineers who analyzed the drawings had seen prototypes for tailless aircraft like the Hortenho 229 and designs for advanced turbojets. But the sheer integration and sophistication of the Weltenhammer airframe, designated internally as the P-177 Long-Range Strike Platform, suggested a level of systems integration that seemed impossible for a collapsing economy to achieve. Its implications frightened both sides, because if it had been real, it could have rendered existing strategies obsolete overnight. For the Allies, the entire strategy of strategic bombing rested on the premise that their bomber fleets could not be intercepted by anything faster than a piston-engine fighter, and that their home bases were safe from German retaliation. An operational P-177, fast, long-ranged, and potentially difficult to detect, would dismantle that security. For the Axis, the P-177, if real, offered the slim chance of striking directly at the sources of Allied power, silencing the critics in the Reich who called the Wunderwaffen a myth. The stakes were nothing less than the operational integrity of the entire Allied war machine. The technical sections of the sealed container provided the chilling details of the P-177, the atmospheric component of the Weltenhammer system. This wasn't merely a fast bomber, it was an integrated system designed for a singular mission: deep penetration strike with minimal risk of detection. The document outlined the components of a truly revolutionary aircraft project: a tailless, swept-wing airframe with radar-deflecting surfaces. The design was immediately shocking. It lacked the conventional tail surfaces, vertical and horizontal stabilizers common to all existing aircraft. Instead, it was a smooth, blended wing body design, heavily inspired by the aerodynamics research of the German Horten brothers. The swept wings were designed for high-speed flight, pushing the boundaries of transonic aerodynamics. But it was the subtle, annotated details about the surfaces that captivated the Allied radar experts. The engineers had theorized about materials and construction techniques, specifically the use of plywood bonded with activated charcoal, designed not merely to be lightweight, but to absorb and scatter radio waves. The plan hinted at the concept of low observability, what would later be known as stealth. The smooth, tailless form lacked the sharp corners and right angles that were the most potent reflectors of the contemporary Allied radar systems. The Germans were already thinking about how to defeat the enemy's primary defense system before the enemy even fully perfected it. A hybrid propulsion system combining early turbojets with a high-thrust rocket booster. To achieve the necessary speed and altitude for its mission, the P-177 couldn't rely solely on existing jet engines, which were often temperamental and slow to accelerate. The plans called for twin Jumo 004 turbojets, the same basic engine used in the Me-262, for cruising and landing. But for a high-speed dash across enemy airspace and quick ascent to altitude, the aircraft would use a secondary Walter HWK-109 rocket engine, similar to the one used in the Me-163 Comet Interceptor, for a massive, temporary boost. This hybrid concept offered two critical advantages: fuel efficiency for long-range travel and a burst of Mach speed acceleration to evade interception, a level of performance that Allied propeller-driven fighters could never match. A weapons bay capable of carrying a guided, standoff munition. Unlike standard bombers which dropped gravity bombs, the P-177 was designed for precision. Its payload was designed to be released far from the target zone, beyond the immediate range of local air defenses. The drawing showed a small internal bay dedicated to a single, specialized weapon, the BV-246 Hagelkorn Hailstone guided munition. The BV-246 was a radio-controlled glide bomb with wings and a conventional warhead, designed to be released at high altitude and glide over great distances toward its target, controlled by a dedicated operator in the strike aircraft. This was the core strategic concept. The P-177 would penetrate deep into Allied territory, release its guided payload while still flying free of the heavily defended target area, and immediately turn back, drastically increasing crew survivability. This standoff capability was yet another feature that would define tactical air power decades later. And a control system that hinted at primitive electronic stabilization. The tailless design presented immense challenges to flight stability. To overcome the inherent instability of the swept wing, the plans incorporated detailed drawings for primitive gyroscopic sensors and electro-hydraulic actuators, an early form of what would later become fly-by-wire, or electronic flight control augmentation. These systems were necessary to keep the revolutionary, aerodynamically challenging aircraft controllable for a human pilot. None of these elements were individually shocking. Germany had experimented with all of them. The Horten brothers built tailless gliders, the Me-262 used jets, the Me-163 used rockets, and the Fritz X was a guided munition. But the combination was decades ahead of its time. The P-177 represented the total system integration of these disparate technologies into a single, cohesive, long-range strike platform. What truly terrified the analysts was that the design resembled the blueprint for a low-observable strike aircraft, a concept that wouldn't be realized by any nation until the late 1970s. This German blueprint, drawn on wartime parchment, contained the genetic code of the B-2 Spirit and the F-117 Nighthawk. The enemy, even in its death throes, had been thinking 3 generations ahead, fundamentally challenging the entire future trajectory of air warfare. The P-177 was not ultimately built due to crippling shortages, but the preserved paper trail proved that the intellectual possibility had existed. The Allies, having defeated the German military, now faced the daunting task of defeating German engineering genius, a genius that now belonged to them, but also posed an immediate, terrifying question: what other nation could develop this next? The seeds of the Cold War arms race had been sown. The discovery of the P-177, or Weltenhammer airframe, blueprint did more than provide technical insights. It forced a radical, immediate recalculation of post-war military strategy for the three emerging superpowers: the United States, the Soviet Union, and Great Britain. The collapse of air superiority. The P-177, designed to penetrate deep into hostile airspace virtually undetected, revealed a fundamental vulnerability in the existing air defense structure. Allied superiority in the air during World War II was based on radar detection and the speed of conventional piston-engine fighters. The German blueprint showed a way to defeat both. The low observable surfaces and the high-speed rocket boost meant the aircraft was designed to operate above the effective ceiling of most Allied fighters and below the threshold of reliable radar detection. For the analysts, the implication was clear: air superiority, the bedrock of Western strategy, was fundamentally temporary. Future air wars would be defined not by the speed of the interceptor, but by the invisibility of the bomber. This realization prompted an immediate, highly classified review of existing Allied defense technologies. The US and UK began prioritizing long-wave radar research and the development of new, high-altitude jet interceptors capable of matching the P-177's projected performance. The concept of layered defense, a mix of ground radar, air patrols, and anti-aircraft artillery, was deemed insufficient against the threat of a low observable, high-speed penetration. The American response: secrecy in R&D. For the United States, the primary reaction was to ensure the complete intellectual quarantine of the P-177 concept. The project was classified at the highest level, accessible only to a tiny fraction of engineers and military planners. The fear was that if the Soviet Union discovered the full scope of the low observable concept, they would accelerate their own research, creating a terrifying strategic imbalance. The blueprint immediately informed two critical, decades-long American R&D paths. High-speed aircraft. The swept-wing and hybrid propulsion concepts were integral to early American high-speed experimental aircraft, pushing the limits toward Mach 2 and beyond. The German work on transonic flight dynamics, evident in the P-177, became the backbone of early American jet research. Low observability research. The charcoal plywood absorption concept, though crude, proved the principle. This led directly to decades of highly secret research into radar-absorbent materials, RAM, and aerodynamic shaping that minimized radar cross-section. The F-117 Nighthawk, developed nearly 40 years later, was the ultimate, direct technological descendant of the P-177. The Soviet drive, catch-up and overcompensation. The Soviet intelligence teams, though denied the original P-177 plans, were aware of the general scope of advanced German concepts. Their reaction was one of intense technological paranoia and a commitment to overcompensation. Lacking the full conceptual details of the P-177's radar-deflecting surfaces, the Soviets focused on mass and speed, creating aircraft that relied on brute force rather than subtlety. They developed massive, powerful engines and focused their air defense strategy on sheer volume, building thousands of powerful interceptor radars and deploying aircraft with massive cannon and early air-to-air missiles, assuming that if a low observable aircraft existed, their only defense was to fill the sky with enough destructive power to guarantee a hit. The P-177 blueprint, therefore, set the tempo for the Cold War air race. It created an enduring, mutual state of technological anxiety, the fear that the enemy was always one step ahead, holding a secret that could negate billions in defense spending. The silent, advanced concepts detailed on the brittle German parchment were the genesis of the decades-long push for hypersonic flight, electronic countermeasures, and, ultimately, stealth technology. The abandoned German laboratory had yielded not a weapon, but the strategic foundation of the next 50 years of warfare. The discovery of the P-177 long-range strike platform blueprint, the atmospheric component of the Weltenhammer concept, did not merely intrigue Allied analysts, it caused a profound, immediate panic that rippled through the highest echelons of the military command structure in London and Washington. It was a panic rooted in the terrifying realization that their fundamental wartime strategy might have been resting on a dangerous illusion of security. For the Allied command, the fear was immediate. It hinged on a single, vital question: how far had the Nazis progressed? The blueprint was a design for a revolutionary aircraft, but was it merely paper, or was there already a factory somewhere, deep in the mountains of Bavaria or concealed in the forests of the East, stamping out the parts? The entire strategic effort of the war depended on the answer. The core of the anxiety lay in the potential mission profile of the P-177. If operational, it could have struck deep behind the front lines, bypassed radar nets, and targeted ports, supply depots, and bomber airfields with near impunity. Consider the strategic implications. Disruption of logistics. The invasion of Europe, Operation Overlord, and the subsequent drive across France depended on massive, uninterrupted supply lines flowing through ports like Antwerp, Cherbourg, and supply depots in the UK. A single, low-observable P-177, armed with a powerful conventional warhead or even a chemical payload, could have devastated a crucial port facility or a vast supply depot, crippling the Allied advance for weeks. Destruction of air superiority. The air war was won from massive bomber airfields across East Anglia and Italy. The P-177's speed and stealth capabilities meant it could have conducted a sneak attack, destroying rows of Park B-17s and Lancasters and demoralizing the bomber crews. The psychological impact of being attacked deep within the secure zone would have been immense. The collapse of radar defense. The Allies had perfected vast, layered radar chains, notably the British chain-home system, which were designed to provide crucial minutes of warning for incoming raids. The P-177's design, the smooth, tailless form and the use of radar-absorbent materials, was specifically intended to defeat this system. If it could penetrate without warning, the entire defense structure of the Allied home front was suddenly obsolete. The intelligence teams reacted with a massive, coordinated effort. The Allies rushed to cross-reference the blueprint with captured factories, test ranges, and research logs. This became a central focus of the T-Force teams still scouring the Reich. They weren't looking for finished aircraft. They were looking for evidence of the production pipeline, the specialized tools, the unique material orders, and the logistical planning that would betray the project's physical existence. The search was exhaustive. Material traces. Teams checked metallurgical labs for orders of high-grade, heat-resistant alloys necessary for the rocket booster's throat. They scrutinized chemical inventories for the precise resin compounds needed for the ablative shielding and the charcoal plywood mixture for the stealth surfaces. Factory floor evidence. Analysts compared the unique geometries of the P-177's components with specialized, one-off machining tools found in underground factories like the one at the Mittelwerk where the V-2 was produced. They looked for evidence of the colossal jigs and molds needed to shape the large, complex swept wings. Personnel interrogations. German engineers captured under Operation Paperclip were grilled relentlessly on the existence of the P-177 Weltenhammer program. The compartmentalization of the German scientific effort was so severe that many key V-2 engineers genuinely had no knowledge of the specific P-177 airframe, heightening the Allied fear that the project had been hidden in a totally separate, highly secure complex. The final conclusion offered a fragile, anxious reprieve. No completed prototype was ever found. The Allied bombing campaigns and the successful strangulation of the German supply lines had performed their crucial function. They had killed the Wunderwaffen in the cradle. However, the intelligence was far from reassuring. Fragments of airframes, wind tunnel mock-ups, and component orders suggested that the project had progressed further than anyone had realized. In a decommissioned Messerschmitt factory in Austria, technicians found partial jigs designed to hold large, complex wing sections that did not match any known German aircraft. In one research log from a test center in the Baltic, analysts found records of high-speed flight tests of small, dynamically similar tailless models, confirming the Germans had solved the basic aerodynamic challenges of the swept wing, tailless configuration. Most crucially, orders were found for specialized, high-purity graphite electrodes, essential for the intense heat and pressure required in the rocket engine's combustion chamber. These orders indicated that the rocket booster itself was moving from the drawing board to the foundry. The overall assessment was chilling. The P-177 was perhaps 6 to 12 months away from a first test flight when the war ended. The collapse of the Reich had occurred just in time. The American and British high commands knew they had dodged an extinction-level military threat, but the intellectual concept, the blueprint for stealth, was now a captured secret, and it immediately began dictating the defense strategies for the next conflict. In a strange twist of history, the panic over the P-177 was not confined to the Allied capitals. Declassified post-war interviews show that even high-ranking German officers were unnerved by the concept, viewing the relentless drive for such complex, futuristic weapons as a symptom of the Führer's final, destructive madness. The German war machine, by 1944, was running on fumes, desperation, and forced labor. The idea of a massive, multi-billion-mark project like Weltenhammer consuming the last viable engineering and material resources was seen by many pragmatic officers, especially those in the Heereswaffenamt Army Ordnance Office, as the ultimate act of strategic sabotage. Many feared that such a complex weapon would drain desperately needed resources from existing aircraft programs. Why invest the remaining supply of precious alloys, high-grade electronics, and skilled manpower into a project that wouldn't deliver for a year, when existing, proven aircraft, like the Mi-262 jet fighter, were desperately needed to defend the collapsing German skies right now? Field Marshal Erhard Milch, the chief logistics officer for the Luftwaffe, was reportedly furious over the constant diversion of jet fuel and key personnel to exotic projects with no immediate tactical payoff. The P-177 and the A-9/A-10 rocket demanded perfect manufacturing conditions, which simply did not exist under relentless Allied bombing. The attempt to manufacture components in hastily built, dark, damp underground factories led to inevitable quality control failures, making the final assembly of such complex systems an engineering impossibility. Others worried it could provoke Allied retaliation if intelligence of the project leaked. The German leadership was keenly aware that the V-1 and V-2 attacks on London had stiffened British resolve and led to a massive, concentrated Allied bombing campaign against rocket launch sites and production centers. The thought of the Allies discovering a project aimed at the American mainland, the P-177 was clearly designed to deliver a warhead to North America, terrified the more rational German military leaders. They feared it would invite a final, vengeful, and overwhelming bombardment that would obliterate what little German industry remained. The doubt of the creators. The deepest unease, however, resided not with the generals or the politicians, but with the men who held the pencils, the engineering teams themselves. The technical genius of Dr. Hans Müller and his colleagues was undisputed, but their reality was one of constant, crippling failure due to external factors. Most importantly, the engineering teams themselves doubted they could actually build the aircraft with the materials, machining tolerances, and electronics available in 1944-45. The technical challenges were overwhelming. Machining tolerances. The turbojets and the rocket booster required tolerances measured in microns for the turbine blades and combustion chambers. These precise measurements were impossible to maintain using rushed, outdated equipment operated by exhausted, malnourished workers. A single misaligned part could lead to catastrophic engine failure at high altitude. Electronic stabilization. The P-177's tailless, high-speed design necessitated a primitive electronic stabilization system. This required complex gyroscopes and vacuum tube circuitry that had to function flawlessly under immense vibration and G-forces. German production of reliable electronic components had plummeted due to bombing and material shortages. The engineers knew a human pilot could never reliably control the P-177 without this critical electronic augmentation, and they simply could not guarantee its reliability. Fuel and materials. The P-177 required vast amounts of specialized, high-test kerosene jet fuel and liquid oxygen for the rocket booster. Germany was virtually out of petroleum, and its capacity to produce liquid oxygen was constantly compromised. The design was magnificent, but the logistical reality was starvation. The P-177 was a weapon ahead of its time, too advanced even for its creators. It was a testament to the power of pure scientific thought, but a victim of the brutal reality of wartime logistics and industrial collapse. The blueprint was a magnificent piece of future history, trapped in the impossible present of 1945. The survival of the Allied cause, therefore, was secured not just by Allied bombs, but by the essential industrial weaknesses of the Reich itself. The Weltenhammer blueprint serves as a chilling reminder of the thin margin of victory, a victory that came before the Nazis could fully translate their terrifying genius from paper into the sky. The paper blueprints were secured, but the intellectual threat remained, and it would immediately inform the anxieties and strategies of the dawning Cold War.